Hello, so today we are going to introduce our literature review on autism diagnosis. We based on the original paper about activity-based early autism diagnosis using a multi-dataset supervised contrastive learning approach. So I'm Kelvin, and my group member is Tiancheng Qin. The agenda today includes a brief introduction of the paper, the background knowledge and techniques which the research in this paper is based on, some proposed approaches from this paper, a design of the experiment here based on two datasets, the hand gesture dataset and the autism dataset, a summary of the experiment's results, and finally a conclusion of today's presentation. So today I'm going to introduce what is ASD. ASD, as known as Autism Spectrum Disorder, is a neurological disorder affecting social interaction and communication. The symptoms typically appear in early childhood of a person. The mean age of diagnosis of a person is typically late. It is difficult to diagnose in early childhood. It is time-consuming and error-prone diagnosis, and therefore lead to delayed treatments. As a result, young-age children need multiple visits to a human specialist. The proposed solution in this paper includes an automated diagnosis of ASD, which includes a multi-dataset contrastive learning on video data. One challenge of it is about a limited amount of training data, which leads to poor accuracy. Another challenge of it is about low interclass variability, which leads to ASD and control samples being visually very similar. We have two common techniques based on previous researches about autism diagnosis, which includes firstly, data analysis based on visual cues of the patient. The patient might have an atypical site, such as the misalignment of eyes. Researchers typically focuses on patients' visual bias on different objects, contrast, or colors. And secondly, the introduction of the hand gesture dataset introduces short video clips of predefined activities done by a patient versus a person without ASD in a weakly controlled environment. Moreover, we have a single-step classifier with different modalities, which integrates multiple data types or sources in one classification process. Also, we have binary classification on multiple datasets, such as the use of a sample-level binary classifier like SVM or neural networks. In general, the advantage is an improvement of feature representation, which also improves the training performance and minimizes the issue of domain shift across different datasets. Specifically, we know that there are recent successes of contrastive learning techniques. Contrastive learning aims pulling similar samples closer. Unimodal self-supervised learning, such as SSCL approach, includes a given sample, as known as an anchor, as well as its transformed version, obtained by some non-learned transformations. For example, horizontal flip. It generates the negative pair using the same given sample and any other samples, either from the dataset or the transformed version. Multimodal self-supervised learning, such as MSSCL approach, involves cross-modal positive pairs. Finally, external supervised learning, such as SUPCL approach, is in the form of category labels. It suits the problem of ASD diagnosis. Input data contains paired samples from two different modalities, such as video and audio, that are extracted from an audio-video recording. The challenge is that not always feasible to obtain paired data. Moreover, there are some further applications on object detection and image segmentation as well. The diagram below gives a brief summary and a comparison about what other researchers have done on this domain of ASD diagnosis, as well as what researchers in this paper did.
Now, let me introduce you to the author's proposed method M-subcell, whose main process is to learn a deep feature encoder network and then train a classifier for a specific dataset. For a batch, we generate pairs for each sample in the batch with other samples in another dataset. If they share the same labels, then we mark them as positive pairs, and vice versa for negative pairs. This is done to obtain all possible pairs in a given batch, help the network learn to distinguish between the different classes and pairs to calculate the contrastive loss. So, what do we need to do for feature extraction? We need to train a feature encoder network to map video features to a high-dimensional feature space. Here, they use the ResNet-based network to generate the embedding vectors. Afterwards, these embedding vectors are used to compute the contrastive losses, and these contrastive losses are used to update the encoder network with the gradient descent algorithms. Finally, a fully connected classification layer is used to make the prediction for a specific dataset. And this is the M-subcell loss equations. In these equations, A means an etcher from the batches, and PA means a set of all positive pairs of an etcher A. KA means a set of all positive plus negative pairs of an etcher A. And Z means the feature embedding of A's, and ZP, ZK just means embeddings of positive pairs and all pairs of etcher A. And the tau means temperature. And the goal of this loss function is to bring the positive pairs closer and while distancing the negative pairs. The author notes that this loss function modifies the supervised contrastive loss function to be applied to multiple dataset setup. For this experiment, they selected two public video datasets, hand gesture and autism dataset. These videos will then be keyframed to generate a pre-processed dataset. The authors next apply several different contrastive learning techniques to this dataset, and compare how these approaches change the model's performance. And the traditional deep learning classification method is used as a baseline, which is using the cross entropy as the loss function.
The first dataset is the hand gesture dataset. These videos will record the kids' 4 activities, which includes placing, pouring, pass to place, and pass to pour. It contains the 19 autism spectrum disorder kids and 20 control groups. It has a high interclass and low interclass variability, which means usually the difficulty to distinguish the difference between two classes visually. The second dataset has the video recording of 8 activities. Each activity is recorded from 2 camera orientations. On the slides, you can see different kinds of activities being recorded in the dataset. One of the challenges in the dataset is that video record both tutors facing and children's facing. The 2 classes in the dataset are more different and better distinguished.
As one of the experiment results, TSNE visualization, which shows how each approach visualizes the data in the feature space. As the first row, you can see the features of gesture dataset with the past approach are very difficult to classify. But the M-subcell successfully to build a boundary between 2 classes in the 5th diagram here. And the features of the autism dataset are very easy to distinguish in area approaches, and the M-subcell also works well. Here is the evaluation matrix of the experiment. So the average accuracy of the author's method on the hand gesture dataset is significantly higher than that of traditional binary classifier and other contrastive learning method. It reached 84%. And on the autism dataset, accuracies of various methods are close to perfect, and the M-subcell has an average accuracy of 99.07%, which is slightly less than the other method, but it performs well on the hand gesture dataset, which is more difficult to classify. And here is the confusion matrix of the M sub CL in the hand gesture dataset. We can see it have really no false positive and false negative.
In summary, the MSUPCL approach effectively improves the classification ability of the traditional model in this task from different datasets but with similar tasks. By learning useful feature representations from an easy to classify dataset, the MSUPCL approach can transfer this knowledge to harder to classify datasets, and thereby improving overall classification performance. Another advantage of multi-dataset learning is that it reduces the problem of domain bias between different datasets. That's all of our presentation. Thank you.